Ravi Shraddha.
A very warm good morning to all the participants. I, Ravi Gatti, Assistant Professor, Department of Electronics and Communication Engineering, Sri Venkateswara Engineering College, Bangalore. We welcome you all for the second day AICTE sponsored short-term training program under AQIS program on optimization techniques for 5G cellular networks. This program has been organized by the Department of Electronics and Communication Engineering, Sri Venkateswara Engineering College, Bangalore, Karnataka. In the day one, we had two sessions by the keynote speakers, Dr. Suresha sir, Principal, SVCE Bengaluru, and Dr. Dilip Reddy Bolla sir, Associate Professor, Department of Electronics and Communication Engineering, SVCE Bengaluru, highlighted on the introduction and integration of 5G with IoT technologies. Today, we go one step deeper in understanding and to know the wider technological concepts of 5G. For the today's morning session, we have Dr. M.H.Kori, IETE Distinguished Fellow, Retired Technical Director, AlcatelLucent Technologies, Technology Consultant, TSDSI, former Chairman, IMAPS, India, on a research topic called as Technologies Driving 5G and Optimization Using Artificial Intelligence and Machine Learning. On behalf of management, principal, and head of the Department of Electronics and Communication Engineering, we welcome you, sir, for this event, sir. I would like to introduce the session speaker to the participants with a brief profile. Dr. M.H.Kori is one of the leading wireless and mobile telecommunication and RF expert. Sir has more than 40 years of experience in telecom, RF, microelectronics, and IT. Sir research, industries, and academic experiences includes at AlcatelLucent Technologies as Technical Director and also as a Head of Hyderabad R&D Unit, Head of Wireless Division C. VP Geosoft Technologies, Head of Telecom DSQ Software, IIT Bombay, University of Duisburg, Germany, Advisory Validus Technology USA, Consultant TSDSI. Their professional contributions includes extensive research work in wireless and mobile communication, head of the architecture team in AlcatelLucent Technologies, working on many technologies leading to 5G, digital microwave developments at C. Visiting fellow at University of Duisburg, Germany, distinguished MMIC chip fabricated at Daimler-Benz MMIC Foundry, Germany, member of several advisory and standard committees such as Study Group NWG9 of ITUR guided students for MS and PhD at IIC and other institutes. Member of Advisory Committee, Academic Council for many institutes and universities. Sir has published and presented many papers in international journals and conferences, conducted workshops at national and international conferences, and has been a chair, co-chair for several conferences, co-author, contributed editor and co-editor of books, conference proceedings. His recent invited talks includes talks at IEEE panel discussion on 5G for India, invited talk on 5G at International GIFSI workshop. He is the organizing chair for the International Radar Symposium and International Symposium on Microwaves. Dr. M.H.Kori is an immediate past chairman of International Microelectronics and Packaging Society, that is IMAPS India, past TPC chairman of IETI, past chairman IETE Bangalore Center, past vice chairman of IEEE MTT and ED Society, past EC member IET, is a recipient of RVC World Telecom Day Award and IETE Batra Memorial Award. Sir is a distinguished fellow of IETE and areas of interest includes wireless communication, 5G and IoT, RF and MMIC microelectronics. Dr. Kori holds PhD from IIT Bombay. We are greatly honored and privileged to have you with us, sir, for this elite event. With this introduction, I once again welcome you and request you, sir, to take over the session. Thank you.
Thanks. Good morning to everyone. Thanks for the nice words. I'll be today talking about some aspects of 5G. I'm sure yesterday you have heard some very good talks on the 5G part of it. And also, now there are so many talks on the 5G which is coming up. So, and also I had given some time back, I've also been giving many talks on 5G. So I'm sure you would have heard some part of it. Hopefully, I'll add a little more to what we have been speaking on. So if there are some things which are repetition, people who have heard me or others will have to slightly bear with me because there are so many seminars, webinars going on in the domain of 5G because 5G is right now coming up and is of interest to everyone. So let me see whether I can add some value to it. But of course, there will be certain things which I'm sure you would have heard. You'll have to just bear with me. Thanks. Let me share my slide. Okay.
Sir, make it full
Is my
screen.
slides coming up?
Yes, sir, it is coming up. Make it full screen, sir.
Okay. In my screen, it is not.
It is displayed, sir. It is displayed.
Oh, okay. Okay. Yeah. Let me do that. Thanks.
Okay.
Okay. Okay. Thanks. Yeah. So primarily what I'm trying to talk is about, this is a broad class of technologies, wireless communication systems. So my standard slide is wireless is an expression of freedom. Wireless is the one which gives you that kind of freedom, which is not possible with any other communication technologies. Particularly, eventually, communication technology will be a combination of optical fiber and wireless. These are the two core technologies which will drive all kinds of communications. It could be cellular communication like 1G, 2G, 3G, 4G, 5G related things, or it could be Wi-Fi, it could be personal area networks, it could be any of those things. Eventually, everything boils down to the last mile connectivity will be the wireless part of it, which gives you enormous amount of freedom, and the core network, which will be in optical fiber, which has the enormous capacity of taking up this much of huge amount of data that's coming in the communications. So it's a marriage between core network on the optical fiber and the freedom which you get on the wireless communication systems. So this combination gives a lethal combination of doing communications anywhere, any form, anytime communications. So as you are all aware, before this, I just want to have the disclaimer that most of the material, except certain few things which from my AlcatelLucent research work, other than most of the information which you see are available in the public domain and they belong to all the individual contributors, people who have contributed to it. There is nothing original about these things. This is all available in the internet. If you have the patience and go and search, you will get. What I have tried to do is collect all these information into one form and then so that it's easily available to all of you. As you can see that we have moved from 1G to 2G to 3G to 4G to 5G. As you can see here in this slide that we have moved from, it almost looks like every decade there is a progress which is being made. The term 1G, 2G, 3G is something which comes from a standardization body called 3GPP, Third Generation Participation Program, that decides on the standards, that decides on the interfaces between different components of these communication systems. So that's the one which decides that new standards have come. Everyone who is associated in developing this and making it available to you and me, they have agreed on an interface. So that is the standards, and the standards are done by, for this communication systems, it is done by 3GPP. For wireless LAN, there is something known as the Wi-Fi, and for each of them, the IEEE 802.11 standards, there are several standards which decide on the interface how it works. This is very, very critical simply because it can't be a proprietary protocol interface such that you have to buy everything from one vendor. Now you can buy the mobile phone from one company. The base station could be from someone else. Some other part of the network could be someone else. How does each of them work with each other without any problem? Is the one where the standards bodies come and they define the interfaces. So that's why it is there, and they decide that this is the next generation which is coming. People are talking of fifth generation, beyond fifth generation. Some are talking about sixth generation, but it's all in the air. There is nothing which has been defined for sixth generation, but research work will be going on. As you can see that moving from first generation, which was analog, to second generation to digital, to third generation to mobile broadband, the fourth generation to fast mobile broadband internet protocols, and we have moved into the fifth generation communication system. We'll be going into the details of this subsequently. And same thing you can see in this here also, a different version of the same thing, how we have progressed from first to fifth generation communication system. But there is a significant difference which has happened from third to fourth, fourth to fifth, which is important. From first to second, we moved to digital. That was a major significance. And third to fourth, certain amount of differences which came from fourth to fifth. So we'll just briefly look at some of these things. Depending upon the coverage area, you can also classify as personal area network, local area network, metropolitan area network, wide area networks, and similarly, you can see these things. We have moved from several technologies like Edge to UMTS, Universal Mobile Telecommunication System, to high-speed packet access, to long-term evolution, which is known as the fourth generation communication systems. These are some of the standards, 3GPP standards, how we have evolved. You can see there is one more slide in which I will show that we have increased the throughput, we have reduced the latency, we have reduced the cost per amount of data, and then the kind of mobility we can give with a low mobility to high mobility to very high speed. If you're going in a bullet train also, you can have the communication system. So these are different parameters under which the improvements have happened. We have increased the data rate, we have reduced the latency, we have reduced the cost, we have increased the speed at which the vehicle can move, still the communication can continue. So this is one of the ways in which you can classify how we have made progress in each of those things. This also gives in terms of the peak data rate. Just look at kind of technologies which we had. We had this GPRS when we started GSM, and similarly there were several standards. We have moved from, there were two standards, one from the European side, one from the American side. We have moved from GPRS to General Packet Radio Services to Code Division Multiple Access, Edge, CDMA 2000, Universal Mobile Telecommunication Systems, Evolution Data Optimized, High-Speed Data, Downlink Packet Access, Evolution Data Optimized in Rev A, Rev B, Rev C, and then we moved to high-speed uplink packet access, high-speed packet access, WiMAX. In the WiMAX itself, 802.16m standard. Then we moved on to LTE, LTE Advanced, and then it is now progressing into fifth generation communication system. And good part of it is that in the fifth generation communication, there is only one standard, because all that other time earlier, we used to have two kinds of standards, predominantly from Europe and predominantly from US. So this is how it was moving, but you can see the data rates which have moved significantly here, mobile broadband which has come. Just to go back before I touch upon the fifth generation communication system is how did we move from third to fourth, and what part of it we are continuing from fourth to fifth, and what are the significant differences. It's interesting to observe that when we moved from third generation to fourth generation communication system, we moved the air interface from the CDMA to orthogonal frequency division multiplexing. So that was the you're all familiar with standards. The air interface part of it, one was using code visual access. TDMA based system, CDMA 2000 was based on the code division multiple access. Everyone moved into per se technology.
So due to some network issues, I think this person has been exited. So just wait for 2 minutes. Sorry for the inconvenience caused. So we hope in the upcoming days, so this kind of disturbance may be eliminated. Just few minutes, please bear with us. I just want to notify to the participants that in the afternoon session, we have one more session. This will be handled by Dr. Jijesh DJ, who is an associate professor and IQIS coordinator from the Department of Electronics and Communication Engineering from the College of Sri Venkateswara College of Engineering, Bangalore. So we request all the participants, please join for the afternoon session also. On a topic called as research opportunities, which is related to 5G technologies. Sir will be handling the session on that. Just few minutes. I think sir will be back. So just communicating with the resource person. Within a minute, sir will be joining once again the session. Yes. Yes, sir.
Yeah, I think I'm connected now. Okay.
Yes. Okay, sir.
Yeah, share screen. Okay. Is it visible now?
Yes, sir. Make it full screen, sir.
Oh, okay.
Okay.
Yeah, okay, thanks. I'm sorry, I don't know where I left. I was talking about the air interface, about code division multiple access moving to orthogonal frequency division multiplexing. Is it audible now? It's okay?
Yes, sir. It is audible and we can see it. You can
Okay.
continue, sir.
Okay, thanks. So in third to fourth generation, we moved from CDMA to OFDM. We moved from circuit switching for voice to packet switching for data. We moved from that to all IP network in the core network. That is irrespective of whether it is voice or data. We have moved from there from circuit switching and packet switching combination, which was there up to third generation communication system. We have moved into the core network of fourth generation communication system. All the core networks were in the packet switch network. That's the voice is also now going as a voice over IP. So if you look at your phones in the 4G communication system, you will see it as VoLTE, that is VoLTE, that is voice over LTE networks. That means it is a packet network, it's a data network on which the voice is being used. That means there is no distinction between voice and data, which used to happen in the earlier third generation communication systems and before that one. So that circuit switch, packet switching, which used to happen for voice and data is not happening now. It's all IP networks. That was one of the major differences. And then the building blocks which used OFDMA and distributed architecture and IP-based core network, these were the major changes which were brought about in the fourth generation communication system. And also to increase the spectral efficiency. The spectral efficiency is how many bits can you accommodate in 1 hertz. That efficiency, which was being increased by several other technologies, that was enormously increased by use of technique known as the multiple input, multiple output. So multiple antenna techniques were introduced into the fourth generation communication system, and IP based architecture was brought in. Distributed architecture, I think I have one slide, I'll show that unless in the third generation, up to for third generation communication, it was purely hierarchical network, but moved into slightly distributed networks. So these were the changes which were brought about. And then here you can see that in the network, there was an interface which was built into the E node B, and E node B is some interface known as the X2 interface, which was brought in so that there is a communication happening between the base station. It doesn't have to go into the core part of it and then come back. Any call which is coming from any user, it doesn't have to go all the way down, up and down, pure hierarchical networks. It was a distributed, some part of distributed network. I won't call it as total distributed network, but it's partially a distributed network interface was brought in the 4th generation communication systems. I'll come to that, what is the importance of these architectural changes which are needed, because earlier it was pure hierarchical networks. We are moving from there to a complete distributed network. Hopefully we'll move in the, not even in the 5th generation, probably subsequently in 6th or 7th generation, we will come to a complete distributed architecture where we can talk device to device communication kind of thing. You can see OFDM, MIMO, flat IP, all IP networks. These were the main hallmarks of this 4th generation long-term evolution advanced networks. I'll skip this part of OFDM, most of you know, but you need to appreciate that orthogonal frequency division multiple access is the core air interface access method, which is being used virtually any form of wireless communications you take. All of them use OFDM right now. If you go to Wi-Fi, they use, you go to any radio, satellite-based communication systems, they use OFDM and every part of it. Now, of course, people are thinking in terms of this. These are orthogonal frequency division. What are the non-orthogonals? NOMA, they call it as non-orthogonal frequency. Techniques research is going on, interesting work is going on. But as of now, including the 4th and 5th generation communication system, OFDM is the main workhorse which is being used by everyone. But how it works, I'm sure you are all experts in that area. I'll not get into that part of it. So you can see here we have worked on OFDMA, MIMO, IP core, flat networks. This is how we are working on right now. These are the E-node Bs, and then the IP backbone, and this is the kind of architecture, the 4th generation communication system, which is used. And what MIMO brings, as you are all aware, it increases your spectral efficiency. But I need to mention here briefly that MIMO could be used for increasing the availability, that is to increase the reliability of the system, or it could be used to increase the capacity of the system. It's being used for both of those things. The techniques which were initially started was to increase the reliability, but then we have increased the capacity of the system also. The principle simply, instead of having one antenna transmitting, one antenna receiving, we have multiple antennas transmitting and multiple antennas receiving. And then you can play around with that for various applications. When I come to the 5th generation communication system, you can see some of those things. But it started with the 4th generation communication system with limited number of antennas, but increasing the efficiency of the system. Here you can see here that you have multiple antenna transmitting, multiple antenna receiving, and then you can work around with that. It can also be used for, as I said, for multi-purpose activities. You can also use this for beamforming technology, and MIMO plus beamforming technology, the combination gives you several advantages. And this technology has been extensively used and extended enormously in the 5th generation communication systems. There are some simulations we had done earlier, how the peak throughput, spectral efficiency, latency, all those things. I'll not get into details of these things, but most of you are doing research in this area would understand some of these things. These are some of the resource crates and the frame structure of the 4th generation communication system. But just to remember that it's a 15 kilohertz. There are 15 kilohertz, and then there are subcarriers of this OFDM symbol, the frame structure, all these things. I'll just leave it. But When we moved from LTE to LTE Advanced, there were several other technologies which were introduced: asymmetric transmission bandwidth, layered OFDMA, advanced multi-cell, enhanced multi-antenna transport, transmission techniques, and large bandwidth LTE Advanced. You need to understand that when I say large bandwidth, in the third generation communication systems, it was 5 megahertz was the bandwidth when we used CDMA, and the wideband CDMA. 1.25 gigahertz, megahertz was the one which was used earlier. Now then we moved into 5 megahertz in the third generation communication system. But in fourth generation communication system, bandwidths were defined up to 20 megahertz. Of course, it would depend upon what is the spectrum availability for the operator, but the standard defined that you could have up to 20 megahertz. Since you have up to 20 megahertz bandwidth, your data rate, obviously you can increase the data rate. So some of these things, comparison of LTE to LTE Advanced, I have briefly mentioned some of these things here. Its data rate can go up to higher data rates, and then mobility, many of those things can increase. You could have asymmetric transmission bandwidth, you could have layered OFDMA, semi-persistent scheduling, and heterogeneous networks. That's another important aspect, now broadly called as small cells. Now you could have, there was initial terminology which was used also was femtocells. You could have a cell embedded within a cell. This concept comes simply that everyone is familiar that if you are inside a house, certain portions you don't get signal strength is very is weak, and then you don't have, you'll have to go near the window or the door or go outside or go to the balcony or somewhere else. So how do you address this one? So this femtocell concept was brought in, where it's exactly like any other base station, but with a limited capacity which is put inside. It's like an access, Wi-Fi access unit which is being put, which is a full-fledged base station, but with a limited capacity. That's a very interesting concept. You put the small base station inside your house or inside your campus or somewhere, you put it and you get very good communication. The problem comes is that when you move from this femto station, one of these small cells, microcells or femtocells, and move into the broader cell, wider area network, and then you start communicating between the base station which is covering the wider area. The transition between this to this should be seamless. It is not like Wi-Fi, because in Wi-Fi you have, at least as of now, there is effort going on to handovers between Wi-Fi and a larger cellular network. But as of now, if you have a call on the Wi-Fi, or if you have a data network connected in your laptop or mobile phone, you need to transition seamlessly from that to the wider area network. In this, the interface was very well defined, because it is the same network service provider who is giving you here as well as in the femto. So when you move from here to here, you come out from the small cell within your house to the wider cell, you come out outside. The call should not drop, and seamlessly it gets handed over to the wider base station compared to the smaller base station. So this was the basic concept of this femtocell and the small cells, as it is now called. A wider class of cells are known as a small cell. So that cell handover is very, very critical, and that's a challenging decision, because the signal is coming everywhere, and weak signal is also there within the house or within that femtocell. And you have another transmission happening here. The interference management and the handover between these two, that's the critical challenge for the technologies. So that is where the the interesting part comes, and then lots of people have worked on this, and several PhDs are being done on this area, and this is a very interesting area. But the utility is, you understand that if you are inside the house, you still have a very good communication, and then you move to the wider cell outside, you still continue with the same call or connection or data connection you have, you move from one to another one. That's been defined. So that is one part of the heterogeneous network. And the other one is, if you are on another network, then how do you transfer from one call to another? Another network is that you have your Wi-Fi network, and then you have a larger cellular network, the interface between. That's not very significantly improved so far. So it is, the work is, a lot of work is going on in the fifth generation communication system also. So these are some of the important aspects of the technologies which have led up to the fourth generation communication system. And then how do we move this beyond, and do we continue moving this, or do we do something else? That is the question which was there when people were thinking in terms of moving into the next level of technology. That is the fifth generation communication system. Here you see that our data demand for the data is increasing exponentially. As you can see, there is a huge demand which is moving. It was not linearly moving, it's moving because the voice demand, if it was used only for voice applications, it would have been linearly increasing. But because it's data, simplest example I always give is that you take a photograph using your old mobile phone at 2 megapixel, and now there are phones which are available at 40 megapixel. It's the same picture which you take, and then load on the network is now 20 times more. That's how this non-linearity of it is increasing non-linearly, the data increasing. Even number of people who are using it doesn't increase, just because you are using new kinds of resolutions for your communication system. High data rates are needed. Now you want high resolution moving pictures, you want to video clippings, and now this talk, it gets uploaded on the YouTube and it gets streamed. The amount of data requirements increases enormously. And of course, obviously, in this unfortunate COVID situation, everyone is using communications, working remotely, giving all these talks remotely. For all these things, you need, because I use right now, I'm connected through Wi-Fi to my service provider. So this, if I'm outside, I need cellular network. So the data requirement on the wireless communication increases enormously because of these requirements. On the backbone network, we have optical fibers. It has enormous capacity of taking it. But that's not true. Same thing for the wireless communication systems. You have limited bandwidth. Because you have limited bandwidth, you need to devise new technologies by which, of course, you can keep increasing the bandwidth, and how we increase the bandwidth will come subsequently. But there are still limitations. So if we don't have too much of bandwidth, there is a major constraint in increasing the data rate. And how do we increase that? Using several technologies. Those are the important technologies which drives the new generation communication systems. And you see this, that there is a huge data demand. So from second generation to third generation to fourth generation, and to some extent in the fifth generation, we keep continuing working on satisfying this unbridled, unquenching requirement for high data rates. So that's one of the driving forces. This is the fifth generation communication system. This is the official logo of third generation 3GPP body which decides. So now we are moving towards the fifth generation. We have moved already in my talk. I'm now moving towards the fifth generation communication system. So when people thought of the fifth generation communication system was, is it going to be one more G? We had 3G, 4G, 5G. So is it going to be one more G which increases? I'm not diminishing the importance of this, but realize that the thrust was increasing the data rate. So we wanted to increase the data capability of this one, whether we continue with that one single-minded quest to increase enormous data rate, which is needed. So are we working on that? Yes, definitely we are working in that connection. This is going to be one more G, a very advanced version of G, the fifth generation communication system, where we want to increase the data rate. That is known as the enhanced mobile broadband. So the first principle or first charter of the fifth generation communication system was continuing with the evolutions which we did. Is it going to be evolution from third to fourth, fourth to fifth is increasing the data rate, enhance the mobile broadband. And that is primary, one of the primary functions of fifth generation communication where we are increasing the data rate. There is no question about it. This is one of the main purposes of fifth generation communication system, come with lots of new technologies, techniques, and other methods by which we can increase the data rate, that is enhanced mobile broadband. But the difference between fourth to fifth is it didn't have that one single point agenda of increasing the data rate. There were two more charters were added to the fifth generation communication system. It is not just evolutionary from fourth to fifth, it's also a bit revolutionary in terms of the improvements that have been made, is that we added in the fifth generation communication system another two charters which are known as massive machine type communications and ultra reliable low latency communication system. Please note that MMTC, massive machine type communication, is not something absolutely a new concept which was introduced in the fifth generation communication system. It was developing under different names at different times for over a long period. This development was happening. Only thing is that 3GPP and ITU, all these bodies recognized the importance of those developments which were happening parallelly in other areas, and then they brought this under the fold of this mobile communication systems. This massive machine type communications is just an evolution of or incorporating Internet of Things into the fold of mobile communication systems. IoT was happening all the time. There was developing. IoT is actually an extension of wireless sensor networks and various other technologies which were happening earlier. These technologies were developing for last 20, 30 years. We have all done work on research on extensive work on these wireless sensor networks, and then it transformed with a larger scope, with improved scope and applications as Internet of Things, and Internet of Things has been brought under the fold of fifth generation communication system as massive machine type communication systems. The communications could happen from human to human, human to machine, and now machine to machine type of communications. So this massive is the operative word. Instead of some large number of sensors which were there, this is huge number of devices. All kinds of devices could be given an IP and a communication capability, and then they get connected, and that becomes a massive IoT and a massive machine type of communication. That's the charter which was brought under the fold of fifth generation communications. And there are several other technologies which cater to this IoT. There is LoRa, there is Wi-Fi, there is Bluetooth, there is ZigBee, various other wireless communication protocols are available. But this has been brought under the 5th generation communication system because mobile wireless connection has a reach everywhere compared to the limited reach any of the other technologies, wireless technologies have. So that's the major advantage, and so it has been brought under that called MMTC. And one more charter was added, that is the ultra reliable low latency communication system. Is the requirements for specific applications need two important factors. Some critical applications need low latency and some need extremely reliable communication system. So how do we ensure that these two are brought? So new standards are being brought under this called URLCC, ultra reliable low latency communication systems. So under the 5th generation communication system, we have three broad charters. One is the enhanced mobile broadband, which is a very efficient system of extension of 4th generation communication into 5th generation communication system, meeting the requirements of huge demand on the data rates. And then the two more is massive machine type communication, catering to broadly, which is called as the IoT and various other applications. And then ultra reliable low latency communication systems. So these charts, I think one or two charts which I'll show you is being shown by everyone. Obviously, I will also be showing any 5G. The joke is that if someone is talking on 5G, if he or she doesn't show these slides, they are not talking about 5G, because these are something which came from both ITU and 3GPP and DTSI. Some of these standards, they brought these slides, beautiful slides here. So this is being used by everyone. Because these are good slides, everyone uses it, but you would have seen these things slides everywhere. Which are it's the triangle where enhanced mobile broadband, you increase the capacity, increase massive connectivity, you bring high reliability and high and low latency. So these are some of the things uh, uh, which has been depicted. Some of the applications are mentioned here. I'll not go into some of these applications. But what we need to understand is that right now we are only some 1% of the eventual 5G applications now visible. We are mentioning here, we still don't know the potential of 5G, how it will be used subsequently. There will be some quarter in which this sudden application will be used, which we have not even imagined right now. But you can see the data rates, 10 Gbps, availability, this is the reliability. Now they are talking of 99.999%. That is, they call it as 3 nines. People are now talking of 6 9 requirements. That is 99.999999 availability. Latency, which has to come to 1 millisecond. It needs to cover completely the bandwidth reduction in network usage. Connected and also other applications like if you're using for an IoT application, sensor networks, and it should have low battery life. I mean, high battery life of large, you put one battery and then you use it for 10 years kind of applications. So low power requirements. IoT devices. Now you can see some of the applications. This is, I think, I don't remember Ericsson as Siemens or someone have made a beautiful chart which I'm using. It's massive machine type communication. You can see here smart meters, smart agriculture, logistic, fleet management, tracking. These are pursued presently with limited understanding what we can use it for. It could be used for many other applications, but important thing is the low cost, low energy, small data volumes and massive numbers. This is important. These are the driving factors. It should be low cost. Obviously, if you're using huge number of devices, the cost should be small. It should be using very low amount of energy, and and uh, and the data which it comes, data by individual element will be very small. I think maybe I'm repeating things which probably yesterday someone must have spoken, other experts must have spoken about the IoT part of it. So very important part of it is that here there is an application where you need to design the architecture of your network for very low data rate, and not that the data is coming very frequently, it's coming at a very slow rate, and the number of devices are large, so the volume, massive number of devices with low data rate applications. Compare that with any other application where you want to do a streaming of 4K video streaming, which you want to do at very high data rate. So these are two contrasting requirements the network has to manage. There is one requirement where there are large number of devices, huge number of devices, massive number of devices, but then individually each of those will be sending a very small amount of data, and that too at not very frequent interval. And the second application is you have a huge data, and then the network has to manage both of those things. The architecture of the network, so that is why I'll be coming subsequently, the concept of network slicing is being brought to manage these things. Why I'm bringing right now is to understand and appreciate the network architecture design becomes so complicated, and right from your frame structure to the complete management of the network, you need to re-look at it. How do you manage efficiently these contrasting requirements which are coming up? And then, of course, enhanced mobile broadband, all the applications which you can see here, from virtual reality to augmented reality to broadcasting to 4K, 8K transmissions, all those things. And then, of course, you have critical IoT applications like in industry, if there is a very fast response that is needed, and then the most common example everyone quotes is the driverless cars, automated cars or vehicles, and then robotic surgery and things like that. And it not be always the remote surgery and things like that. It need not be even so complicated thing. Even for industrial applications where you want to have wireless control, autonomous control of things, where a process change happens, there is a certain temperature increases, beyond that you'll have to modify a certain thing in an industrial application, then you need a reliable communication, ultra reliable communication. And also at certain times the latency has to be extremely small. It becomes industry applications, IIoT, what they call industrial IoT, in the industry what they call it as 4.0, where you automating most of the manufacturing part of it, you need this ultra reliable, very low latency, very high availability requirements for the critical IoT applications. So all these things are being built into it. Please note that all of them have not already been incorporated into the standards and ratified it. Somewhere I will be showing there is something known as the release 15, release 16, release 17 in 3GPP in the standards. People are in the release 15 concentrated primarily on the EMBB, that is high data rate application. Release 16 is looking into the other two part of it. Some parts are, we have clarity in the standards, some parts are being discussed, some technologies are being discussed, and subsequently it will be moving into the next release also. The work has started, but they have not been finalized yet. Just to go back to this 5G requirements, you know a lot. High capacity, high data rate, reduced latency, massive devices. Let's look at now how some of the methods by which each of those things are being addressed, or the importance of those things. I'll just spend some time on this. Taking up the first one, enhanced mobile broadband. We want to increase the capacity. There are some very obvious, simple techniques by which one can increase. You can increase the capacity by adding cell size. You can increase the cell capacity. You can increase the capacity by increasing the number of cells. If you have, it's inversely proportional depending upon the density of users. If you have a large cell, then you can cater to only certain number of people. But if you make it into smaller cells, obviously you are increasing it inversely proportional. You can increase the capacity of each of the cell, and then you repeat number of cells. So you reduce it from 5 kilometers to 2 kilometers, and then you make dense cells. That's one of the methods by which it is being done. And then when I come to other aspects of fifth generation communication system, it automatically becomes necessary to have small cells. We can't have larger cells because of some limitations which will be coming up. Inherent limitations because we are moving into higher frequencies. And you can, of course, increase the sectors. You can most of you are aware that though we say that we have an antenna, omnidirectional antenna, and we are transmitting all over, we don't do that in any cellular system, right from first generation to fifth generation communication system. We make it into sectors. I think I have some pictures subsequently, I'll show that. So we make it into sectors, whether we make it into 120-degree 3 sectors, or we make it into 6 sectors. You can increase the sectors and then increase the capacity. You can add carriers, you can increase the bandwidth. If you increase the bandwidth, obviously you are going to. I mentioned in the third generation we were thinking in terms of 5 megahertz bandwidth, but we moved into up to 20 megahertz. Of course, the spectrum itself is not available. There's always contention between the service providers and the government. What is the spectrum they are giving at what cost? Cost part of it, we'll leave it right now, but the spectrum availability is very, very limited. So if you increase the bandwidth, that's the straightforward method of increasing the data rates. So if you increase the bandwidth, LTE users bandwidth, and then we can do carrier aggregations. If this is the segment of frequency available here, there, can we put them together virtually and then use that? That's the carrier aggregation method. And then we have used the air interface, moved from one access method to another access method to another access method. Everywhere, one of the methods by which we have increased the spectral efficiency, that is bits per second per hertz, in 1 hertz, how many bits we can accommodate. The most efficient method of doing it is using higher order modulations. I'm sure you're all very familiar with modulation techniques and the importance and advantages of using higher order modulation. We have moved from the second generation communication system, which we use GMSK as the modulation. GMSK, which was not the most efficient method. From there, we moved into the QPSK modulation, BPSK, QPSK, and few other modulations. We moved into the QAM, quadrature amplitude modulation. In the QAM modulations, we started with 16 QAM modulations, and then 32, 64, multiples of that we have moved, and now modulation schemes have moved up to, imagine, 1024 QAM. That's a huge amount. Of course, you have to pay a penalty there. Again, the penalty is that its efficiency becomes extremely high. It becomes extremely spectral efficient. But to get the same bit error rate, I mean, quality of service, if you want for the same quality of service compared with the QPSK modulation and QAM modulation, 64 QAM, 124 QAM, 256 QAM, you just compare with any of these QAM modulation, let's say 256 QAM and a QPSK modulation. The amount of signal to EV by N0 or signal to noise ratio in a very generic term, the signal strength has to be quite large compared to a QPSK modulation for the same error rate. same quality of service. You know the curves which are there that you can very easily plot them and then find out for the same, if you say it's 10 to the power minus 3 or minus 6, whatever value you want, for that same quality of service, you want the same quality, then the signal to noise ratio or EB by N naught is different for 256 QAM to QPSK modulation. So that simply means that your range gets reduced. You want the same signal strength, then you can't get larger signal, larger coverage area where you could have got up to 5 kilometers, you will now come to 2 kilometers or 500 meters. So that's the penalty you will have to give in terms of you translate the same thing into signal strength into a coverage area. Then your coverage area becomes smaller. So that's the penalty you'll have to pay. So that's one of the reasons, as I was mentioning, that automatically you're forced to come to smaller cells compared to the other cell. Of course, there is a dynamic switching over which happens that your data rate, depending upon your signal strength, the modulation what is offered to you changes, so your data rate becomes smaller. As you can see, if you move away from the signal signal strength, as you move away from the base station, you can all observe in your mobile phones that the speed at which you receive the signal, the speed at which you receive the data keeps reducing as you move away from the base station, your signal strength falls down. That's primarily automatically the system decides what is the best modulation scheme that you can be provided with, such that you continue to get this data connection, but at a reduced uh, data rate. So that is how this modulation automatically keeps modifying. But at a place where you have very good signal strength, you can get it at very high data rates, which was not there earlier systems, but now it has gone up to 1020. So this is one method by which you can increase the spectral efficiency in terms which is increasing your capacity of the system. System which you can do that. These are all interrelated terms where you trade off between one and another one. And the other technologies which were being used are being used is multiple input, multiple output, and smart antennas. I'll come to that subsequently. And then, of course, other technologies like software-defined radio, cognitive radio, which are incorporated into any of those things. So in the 5th generation communication system, these are the key technologies which have been adopted, which is being adopted, and a lot of research work going on. I just wanted you to understand this is not in any specific order, but you will keep hearing these terms extensively when you start working or researching or studying or teaching any of these things. I mean, in relation to 5th generation communication system, these are some of the very important terminologies. You can call it as buzzwords, whatever it is. NR is the new radio. A new radio has been defined for the 5th generation communication system. The radio which was defined for the 4th generation communication, there have been significant modifications which have been done in the 5th generation communication systems, and that is called as new radio. I have an objection or reservation about being called as new radio. No, that's perfectly fine, but this term, when you call it as new radio, I hear the joke that new technologies, we were working on several technologies earlier also. Some things were called as new technology, and then after 5 years, we were phasing out that product, which was called new technology. You call it as new technology, and then you are stopped working because it has become obsolete. So it's a oxymoron. It's a contrasting term which being used, because now in 2020, if we call this as new radio, it has a significance that it's a new radio. 2025 or 2030, it will not be new radio. there will be something else which will be coming. So it's lack of imagination in calling it as a new radio, but let's accept it because it's been called new radio. Let's go with the word new radio. This is the NR, which is very beautifully architecture has been done nicely, such that we'll be using this in the 5th generation communication and subsequently also. So that's one important thing. And the second is that I have already mentioned about multiple input, multiple output, which was used in 4th generation communication system, but it was used in a limited sense that we'd be using 2x2 radios, antennas, or 4x4, maximum 8x8, or any combination of that. But now we are moving into massive multiple input, multiple output. That is, we will be using large number of antennas transmitting and large number of antennas receiving. Not necessarily all the places will be using large number of antennas for receiving. There could be limitations in the handset or other devices, but at least in the transmission we'll be using large number of antennas. So it's a combination of several antennas being used, which is known as the massive MIMO, massive multiple input, multiple output. This is one of the important aspects. And the other one is I have been mentioning about the lack of bandwidth. It's a spectrum availability. Spectrum availability is a major constraint in all the communication systems. And how do we overcome this is by moving from the traditional frequencies which we were using to millimeter waves. We move into another domain of frequencies, and that is known as the millimeter wave frequencies. And that is one important aspect and significant change which happens in the 5th generation communication system compared to up to 4th generation communication system, where we were confined only to, we were using 700 megahertz. In India, 700 was not used because there was some issue about auction and the cost associated, but we have used 800, 900 megahertz, 1800 megahertz, 21 megahertz, 2100 or 2.1 gigahertz, sorry, up to 2.5 gigahertz we have been using, but these are known as low band frequencies in the below 6 gigahertz. So these are the frequencies, but now people will be using millimeter wave frequencies, which will be in the range of 24 gigahertz, 26 gigahertz, 28 gigahertz, 35, 37 gigahertz, up to 60 gigahertz, and now it's being extended up to even 100 gigahertz. So millimeter waves, which is important. Just for the clarification, millimeter wave simply means when the wavelength becomes 1 millimeter. That frequency is 30 gigahertz. So ideally 30 gigahertz and above should be called as millimeter wave frequencies. We have taken liberty to call even 24, 26, 28 gigahertz as also. It's approximately. So it's also called millimeter wave frequencies. So millimeter wave frequencies is from around 20, let's call it as above 20 gigahertz up to 100 gigahertz. We call it as a broad class of millimeter waves, and that is being extensively now advocated for usage for this cellular communications. Some countries have already auctioned and started using it. Other countries are contemplating on it. And the other one is on the beamforming technology, which is an extension of, not extension, it's a same family under which the massive MIMO or MIMO also comes into the picture. These are known as multiple antenna technologies. So beamforming technologies and active smart configurable antennas, these active smart reconfigurable antennas, beamforming and massive MIMO, we can all put together under one family or a class of technologies which should be used. And then, of course, the dense network, smaller cells, which I have already explained earlier. HETnets, heterogeneous networks, also I have mentioned earlier in my earlier part of the presentation. And then there are few other things known as the full duplex communication systems. Full duplex communication system is when you have a duplex communication system, that means both the parties are talking simultaneously with each other. It's not a simplex communication or half duplex, it's a full duplex communication. In that, you could do it using two technologies known as uh, frequency division duplexing or time division duplexing. You can assign two frequencies, for one for the transmitter, one for the other transmitter. I mean, two people. For person one, you give F1. For the second person, you give F2 or F1 dash, you call it. These are the two frequencies so that there is no interference happening between each of them. Or you could do it with time division duplexing, where you transmit at one time interval one person, the other person at another interval, and then both using the same frequency. That's known as the time division duplexing. Both are being used in the cellular communication systems. Some standards use this, some standards use the other one. But is it possible to have simultaneous communication with the same frequency at the same time? How do you avoid the interference? So that work is going on, extensive work is going on, full duplex communication systems and mobile edge computing, artificial intelligence and machine learning, network slicing, network function virtuality, software defined network. These are some of the things which will be extensively used in the fifth generation communications and beyond the fifth generation communication systems. Just to briefly mention about the NR, that is the new radio access technology, new frequency bands have been identified. We were using, as I had already mentioned about that, we were using frequencies actually below 2.5 gigahertz. We are using most of the frequency below 2.5 gigahertz for most of the cellular communication systems. We are using 800, 900, 1.8 gigahertz, 2.1 gigahertz, up to 2.5 gigahertz. For fifth generation communication system, those frequencies will also be used. There is a classification as below 1 gigahertz, some frequencies which could be used, between 1 to 6 gigahertz. In that itself, there is some sub-classification up to 3-4 gigahertz is one application. And then in the 6 gigahertz band, there is another application which could be used. So these are the sub bands within below 6 gigahertz. The definition is below 6 gigahertz and above 6 gigahertz. Primarily, the technologies involved, device applications, everything, there is not too much of a difference if you go up to 6 gigahertz. There is not too much of a change, except the coverage area. If you use 700 megahertz, your coverage area becomes large. It's inversely proportional to frequency. If you use 700 megahertz, you get a large coverage. But if you go into 3.5 gigahertz, then it's fairly medium size of coverage. If you go to 6 gigahertz, it gets a little limited, but there is not too much of a drastic difference which happens. Unlike if you go into millimeter waves, which is at 24, 30, 60, then the coverage becomes extremely small. There are two factors. One is, of course, in terms of the coverage, inherent coverage that comes because of the frequency. And there are other factors like when you go into higher frequencies, your attenuation becomes quite large. Even small obstructions like the wall and windows and doors and even vegetation, they absorb these energies, electromagnetic energies, and your range becomes extremely small. So that, and also the devices needed for making these frequencies, both in terms of the oscillators, amplifiers, attenuators, everything at that frequency, the design becomes complicated. And it becomes smaller and smaller and compact, but the design is a lot more complicated and the fabrication becomes complicated. I'll not get into the device part of the millimeter wave devices, particularly the RF devices part of it. So once you come into the digital domain, it doesn't make a difference. But at the RF level, at the microwave level, the design becomes difficult. The devices will be designed in a totally different. The material that is used for the design becomes different. What you could do in silicon cannot be done in millimeter waves. It becomes difficult. Of course, people have been trying, but you'll have to go move into other materials like gallium arsenide and indium arsenide, indium phosphide, and various other combination devices you'll have to start using. So the costs were high long back. That's the reason people were not doing millimeter waves, but costs have come down. But it needs precision equipment to manufacture those things. But let's not get into the device part of it, but let's purely confine to these frequencies, and that most of the people are trying to do the fifth generation communication system at 3.4 to 4 gigahertz, 3.4, 3.6 gigahertz, 3.8 gigahertz, around that. And in the millimeter waves, 24 to 29 gigahertz in the band. So the NR, the new radio, has been redefined, has been defined in such a way such that these frequencies are accommodated, and then we'll be doing beamforming support for synchronization of signal, broadcast, various intricacies of the whole implementation of the standards in the fifth generation. One has to redefine all these things, the radio parameters, and one of the important thing is the subcarrier spacing and the symbol duration. Some few slides I think I have. Waveform, they call it as numerology, frame structure, the scalable subcarrier spacing. The subcarrier spacing in the fourth generation communication system was 15 kilohertz. It was fixed, but now it has been defined in a flexible manner, and it has been defined as 2 mu 15 kilohertz subcarriers. Then you can calculate, I think, and you know OFDM, people familiar with OFDM, you know that it needs a carrier prefix. So the intersymbol interference is avoided. The carrier prefix could be the normal or extended, which was not, these flexibilities were not there in the fourth generation communication system. You can see that subcarrier spacing, now it's not necessarily 15 kilohertz, it is 15, 30, 60, 120, 240. These have been defined so that there is a flexibility. Depending upon your data rate requirements and whatever demand that is needed from the user, you can flexibly choose this subcarrier spacing. It could be, and also these larger ones, I think you can see, this is defined only for millimeter waves. I think I have a slide here. Numerology represents 15 kilohertz, that formula which I showed you here. You can define that parameters, and then as you can see here, LTE, there is only one type of subcarrier, that is 15 kilohertz, whereas in NNR, multiple types of subcarrier spacing available. There is a flexibility, so that the people who design and the system can choose depending upon the requirement. It can choose these things, and then you can calculate waveform up. You can see here that below 6 gigahertz, it's defined up to 60 kilohertz of carrier spacing, and above 6 gigahertz, these really wide subcarrier spacing is permitted here under the standards. It's a 120, 240, 480 kilohertz. These have been specified, but some of these things were implemented in release 15. Some moved into the 16. I'll come to some standards. You can see that frame and subframe downlink uplink transmissions, they are defined. I'll not get into details. People who are serious about it, who are really working, I'm sure they know about it, or it's available everywhere. This information is about. You can see that the frame and subframe structure, how it has been defined, the frame 0, frame 1, and each frame obviously has 10 milliseconds, and then that 10 milliseconds is divided into subframe from 1 milliseconds, and then and there are slots lengths which is defined. I'll not go into details of this, how it can be done, but what you need to know is number of slots per subframe varies with carrier spacing, and there can be 16 slots per subframe, and in LTE there is no fixed 2 slots per subframe, but in NR the number of this one is available. So you can see here, and then this is the details of how the subframe with 1 millisecond, how it is divided into different slots for different carrier spacing. For 15 kilohertz, how it is done, and for 120 and to 240 kilohertz, how it is done is shown here. This is available. Open literature, this is available, this information is available, and in the OFDM, how it is carrier prefix and other things which have been done. All the information about the NR is available, and this is also available here. And this gives the coverage comparison, which I had mentioned, that below 1 gigahertz, up to 6 gigahertz, and above 6 gigahertz. You can see here that above 6 gigahertz only NR is the one which you will not be able to, because it was not defined in the earlier version. It was not defined, NR was not there, so millimeter wave was never used in the earlier generation communication systems, mobile communication systems. In the 4G, here we have both NR and LTE available, but you can see coverage becomes slightly limited. And here the coverage is quite large, but the bandwidth available is less. So the capacity gets constrained, your coverage becomes increased. So you have to have a trade-off between your coverage and how much capacity you would be able to do that one. And actually, this is a fairly good trade-off between the coverage and the capacity. So everyone is looking at these frequencies around 3.5 gigahertz. Most of the applications will be in that range, but real capacity increase will come when you go to millimeter wave frequencies. Just imagine you want to get 20 megahertz in 700 megahertz as the your carrier frequency is 700 megahertz. 20 megahertz is a huge fractional value. It's a significant value because frequency is being shared by hundreds of agencies. So you're getting 20 megahertz, 50 megahertz, or 100 megahertz, which is an absolute luxury. It's impossible. 100 megahertz in 700 megahertz. Can you imagine getting it for exclusively for your applications? It's just impossible. There is no way you can do that. To some extent, you can get a slightly larger bandwidth around 3.5, that is 3,500 megahertz, 100 megahertz. The ratio is slightly smaller, but it's still difficult. Everyone wants to use this one. But let's say when we move to, just for example, I take 30 gigahertz. Usually it's around 24 gigahertz, 24,000 megahertz. Imagine in 24,000 megahertz, you getting 100 megahertz is not too difficult. Of course, there are complications because there are certain windows in which only you can use, and a lot of people want, satellite wants to use, and someone else wants to use, and there are other objections. Leaving those things aside, just simply look at the ratio of how much is the bandwidth you need compared to the center frequency of the carrier which you are talking. If you are talking of 700 megahertz and you want 100 megahertz, it is 1 by 7. But if you want 100 megahertz in 24,000 megahertz, then it's not a significant value at all. So the amount of bandwidth that is available in millimeter wave frequencies is enormous. So you can easily get large bandwidths and the associated all advantages which I have mentioned in the requirement of large bandwidth, we always get that one. But how do we get this? At the cost of the coverage area. And also, if there are obstructions, you will have to overcome that. If there is some obstruction, even where you have a window or glass or some such thing which the low frequencies can easily transmit through without much of an attenuation, millimeter waves gets attenuated significantly. And particularly if there is a vegetation, there is moisture, there is certain such obstructions anywhere, it gets attenuated enormously. So one has to design in such a way that those things are taken care, and you have large number of base stations where you have small cells, then millimeter wave becomes advantageous. So obviously there are certain trade-offs one has to look at it, but you get huge bandwidth coverage, so not coverage, bandwidth in millimeter waves frequency at the cost of the coverage. So some of the techniques which have to be used, which become almost mandatory to use in millimeter waves, are these technologies of the massive MIMO and beamforming. They become almost critical, which were just adding, enhancing the efficiency of a system at low frequencies, but you could work without them also in the low frequencies. When I mean low frequencies, it's around 900, 800 megahertz or 2.1 gigahertz or 3.5 gigahertz. But if you move to millimeter wave frequencies, it's almost becomes mandatory that you need to have these technologies like massive MIMO and beamforming when you move into millimeter wave frequencies. These are the coverages, and then some of the beamforming technologies I'll briefly mention. Massive MIMO is number of antennas what we want to increase. You can see here that multiple antenna technology, which if you look at the basic Shannon's theorem, and then if you use MIMO and then adaptive antenna and reconfigurable beams, the beamforming technologies, these are the technologies which play around with the basic concept of how do you communicate, and then play around with that which different parameters. Not getting to the mathematics part of it, but you can play around. You can see the additional channels which is created in MIMO. You can see signal to noise ratio, improving in adaptive antennas and reconfigurable antenna. Also, you optimize those things. So these are some of the ways in which you can work on these things. I'll spend a little bit time on how am I doing on the time. It's okay. I think maybe I'll take another 10-15 minutes. Is it okay? Am I audible? Uh, Hello?
Yes, sir, you are audible, sir.
I just want to know whether I'm audible or not.
Yes, sir, you are audible, sir.
Okay, okay. Could I take another, how much time can I take? Another 15-20 minutes?
Yes, sir, you are
Okay.
always welcome, sir.
Okay, okay, thanks. Yeah. Okay. Yeah, I was mentioning about how do we increase the capacity, and then how do we increase uh, the signal to noise ratio and additional carriers and channels, and optimize these things which we are working on. We increase the multiple antennas. So multiple input, multiple output antennas are where you use, instead of using one antenna transmitting, one antenna receiving, you are increasing it by the number of antennas which are as I always mentioned that, of course, we can go into the mathematics part of the complete mathematics part of it. Here, it's simply that we are creating, if we are looking at a series or a set of equations, it could be linear, non-linear, let's not get into that. If we are doing a set of equations, if you have only one equation, and then you have multiple variables, you will not be able to solve that equation unambiguously. So you have to create several equations, independent equations, which are not correlated with each other. If you have independent equations, and then you use that to solve these variables, how do you create these equations? You create it by creating large number of antennas, transmitting and receiving, and then if you have those things, then you can solve this equation. So you have multiple antennas, which then the channel which is created by it is independent of the other channel which is created. Then you have a beautiful set of equations, and you can solve those things. So you can have diversity, you can have spatial diversity, space and time, the frequency resource, which you can do that one, multiple antenna, multiple input, multiple output are done using this one. And then you can create, initially all this using multiple antennas was used in other, it was not absolutely new thing. We were using it for spatial diversity in even fixed wireless communication system, point-to-point communication systems. We were having two antennas receiving and one antenna transmitting, so that if one of the antennas fails because there is an obstruction or attenuation is more, or whatever reason, the other antenna will be receiving, and so you are increasing the reliability of the system. So that was the space diversity, where one antenna was separated from another by a certain amount of distance, and so that the probability of receiving by one of the antennas at least is higher compared to having one antenna. This is kind of the space diversity which was being used, but now what we are doing is that several antennas are being done, and then you can increase it, as I had already mentioned, for increasing the capacity or increasing the availability. And also, if you have multiple antennas, you can play around with the signal fed to each of those antennas, and then you can create a different kind of beams, and you can steer the beam, and you can play around with the beam. So that is how the multiple input, multiple output works. Not just multiple input output, the beam forming and beam control and all the related activities can be done. And here some examples of an active antenna and passive antennas. And you can see here, you can see that there is a polarization which you can utilize, the dual polarized base station antenna for 2x2 MIMO and 4x4 antennas which are there. And then here you can see there is a change in the way in which the antennas, initially the antennas were passive antennas. Technically, even now the antennas are passive, but the active component is brought very close to the antenna itself. So you bring that radio embedded base station antennas, and then you have a control over everything that you want to do. And if you have multiple antennas with phase difference, you can change the direction of the beam, contour of the beam, several beams you can create. So these are known as the several antennas which are coming up. So I'm working on this. You can create multiple antennas and antennas which are created here. You have active antennas here, and then you can see the reconfigurable beam antennas. You can change the beam position, beam fanning, the beam widths, all those things by playing around with the phase, the number of antennas, and several of those things which have been connected, and then you can do that one. You can see here, these are the active antennas, radio embedded within the radio, within the antenna itself, and then you can work on that. These are reconfigurable beams. I'll not get into too much details on these things. This is an example of massive multiple input, multiple output. You have several antennas which have been connected here, and each of them, as you can see here, each one is an array of antenna. And then there's several of them. And each of the arrays, you can see here that they have a combination of uh, vertical and horizontal polarization. So with playing around with several parameters, you can increase the capacity and then reconfigure the beams. And this is the maximum multiple input, multiple output, which we can create. And this is huge number of antennas being used. And that increases both spectral efficiency and various other parameters you can do. And millimeter waves, I have already mentioned about it, from 30 to 300, but we extend from 20 to 300. We work on that. And then we define spectrum as below 6 and above 6. So there are definitions which have been given. But how do we design a system such that it is compatible, backward compatible? So that's why 3GPP has come with a combination of things known as 5G radio access, LTE evolution, and new radio. So there is something known as standalone 5G system or standalone system and non-standalone system. So anything in the millimeter wave, it obviously is standalone system, and non-standalone system is compatible with LTE, that is the 4th generation communication system. So this is how the definition has been done in that, and the frequencies. Sorry, the frequency as per the earlier release is defined as FR1, which is 450 to 6000, that is 6 gigahertz, 450 megahertz to 6 gigahertz, which is called as the sub 6 gigahertz, and FR2 is 24 gigahertz to 52, but now it has been extended beyond that to 80, 90 gigahertz. So the definitions, but generally when someone says FR1, it is in the low frequency band, that is around 3.5 gigahertz, between anything between 1 gigahertz to 6 gigahertz, and then FR2 is the millimeter wave band. This is the terminology which is being used in the 5th generation communication system. So let me spend a little more time on the MMTC. Of course, is massive machine type communication systems. We have 50 billion devices expected by 2020, and I've already mentioned about large number of devices, low data rate requirements. How do we plan the network and then connect all those things? What is important is how do we do the processing of this communication system? Whether we do the communication system, the processing is done at a central place somewhere in the cloud, or do we do at the site itself? Which is the best way of doing? This is always a confusion, that whether we need to do at a central system or a distributed system. This is true with any networking problem, also in any computer communication or any other computer applications. Whether you want one huge massive supercomputer connected somewhere and it does all the processing and it gives the information to everyone else, or you have distributed computing which is done at every point at the node itself. There are advantages and disadvantages of each of them. Similar thing happens in the mobile communication system also. Where does all this huge amount of processing that we need to do? Because we are doing in MIMO. MIMO means that each channel, it has to get the channel state information, decide how do you do processing, how do you do the MIMO, how do you do the beamforming, all these things, how do you take care of that? The processing that needs to be done, whether I send it to the cloud at central place, the advantage of that is the major advantage is the huge processing power that is needed. The amount of electricity power consumption is taken care in the cloud, and we don't have to spend a lot of power in the at the site itself, so that everything is done there. That's the advantage. But the problem is that you'll have to send it and get back the information. If the time taken, the latency is large and you can't tolerate that, then you'll have to do the processing at the site itself. So it's a compromise between these. So that is why something known as the mobile edge computing has come and everyone is talking about this mobile edge computing, and it's not necessarily used only in cellular communication system. Other communication systems also it is being used, or not just communication system. Other systems are also used in other computer applications. But this is very relevant here, is known as the mobile edge computing. You do a certain amount of computing at the edge of the network itself, and then certain other things you'll have to send it to the cloud. So it has to be a judicial combination between which is not critical, but intense calculations has to be done, processing has to be done. You send it to the cloud where central processing is done. But where the latency is critical, where you'll have to take decisions immediately, then you do at the edge. So that is how the mobile edge computing is done. So these requirements, mobile edge computing, how much of data you store and what is needed, all these things have been decided. I'll not get into too much of details on this, but we need mobile edge computing, and this is one of the operators can open their radio access network edge to other people, and then you can do, and you can see here mobile edge clouds are created, users are here, you can see here, and then there is a certain amount of mobile edge clouds which are created, and they are interlinked and sent to the core public cloud or enterprise cloud. So this is how the architecture is done. It's a combination of both which is being used here. You can see here that there's a huge amount of connected devices. The data comes here, the data and the knowledge, and this is where you calculate, and then artificial intelligence decides what is to be done, and then it comes into the future network. So you need certain amount of machine learning, mobile edge computing, artificial intelligence. So these are absolutely essential now for fifth generation communication system, because fourth generation or earlier networks were reactive. Once the system, there is a requirement which query comes to the network, then it starts finding out. But is it the best way of doing it? Can you anticipate what is likely to come and then be prepared for that one? They have to be predictive, proactive, and anticipatory to enable low latency and high reliability applications. We have said in our charter in the fifth generation communication, ultra low latency and reliable communications. In this part of the charter, we need to make sure that what are the functions which increase the latency or make it unreliable. So find out that in that, if we are making a predictive kind of network where it anticipates from the information or data which has been gathered over a period, you have built a certain amount of data information, and then use that, use the data science part of it and build a certain models, and then use techniques which are available in other part of the technologies of machine learning and artificial intelligence, and use this for a fully functional fifth generation communication system. Machine learning, as it's mentioned here, allows 5G wireless networks to be predictive, proactive, and fundamental in making 5G vision possible. That is particularly the low latency applications. Machine learning go hand in hand, and then because every day there is a huge amount of data coming to the network. In the fourth generation or earlier generation networks, that was never used for predicting what is likely to happen and prepare in advance for that. So that becomes a lot more critical in the fifth generation communication systems. Base station wants to predict what kind of content users nearby may request in the near future. What is the kind of requirements which is there, which is required, and then how do we plan for that one? So we are trying to work on this. This is where the artificial intelligence and machine learning is coming into the picture. This is how I'll not go into details of this. Reliable requires low latency, which we have already mentioned. Massive amounts of data which is available. How do we effectively utilize this system? I'll just give some few examples and close this talk. If you have as I have already mentioned in my earlier part of the talk, that in millimeter wave applications, we need to have beamforming technology. We will have to have beamforming, that several beams are sent instead of one beam, such that the coverage is made sure that it is happening. And for doing this efficient use of beamforming, there are several beams which could be done, which is the ideal form of beamforming. It's not easy to decide, but you can do it by trial and error method of that. You find out the channel state information, and then what is the signal received at the receiver side and how reliable the communication is happening. Find out that and then get the information and then do that. But if you start doing every time an exploratory method of doing that one, then the time taken is large. And if you have a criticality of the latency, then one needs to relook at how do we do this one. So whether we can use some of the new techniques of machine learning and artificial intelligence in beamforming technology, and this has been used effectively by many people, and then people are working on that to this. Just to give you just an idea of what is involved in this beamforming technology is that you need to identify some of these parameters. What is known as the beam index, beam reference signal received power, the distance, position, speed, channel quality indicator, CQI, and historic value of all these things. So once you have all these parameters quantified, these are not just qualitative information, these are quantified information. And if you have a database of all this information which is available, and then use that in an effective manner, for this kind of applications, I have a history of data that this was the best position, then I can choose immediately that beam position quickly and reduce the latency compared to other possibility of trying to reinvent and start finding out the best position at that time. So this is where one example, this is just one example of how one can use the machine learning and the artificial intelligence for an application in a mobile communication system, in fifth generation communication system. This is being worked. There are extensive work. In fact, I'd sent to some few colleges also. ITU has formed, that is International Telecommunication Union has formed one special working group on AI and ML for 5G applications, 5G and beyond applications. So they, every time they come with specific identified area, one of them was this beamforming, and there were other parts in the network also you can optimize in the core network part of it, provisioning part of it, and various other things where you can do a lot of optimization using this machine learning and artificial intelligence techniques. They're opening a challenge saying that this is a problem, you come with a solution, and then we will support some of your research activities. So one can look out for those ITU, if you go to ITU, that is International Telecommunication Union website, and then you look at it, all the some of these things, you look at the work group which is on the AI and ML for 5G. There is very interesting things which are happening. So, but this is a wonderful area. It's not some esoteric research which we are trying to do. It's practical, absolutely needed requirement. How do you reduce the latency by getting the huge amount of data which you have gathered earlier? Network is learning as it is operating, and then find out. Some of these are the parameters. There are several other parameters for networks, and then you find out and then enhance the way in which the system works. So I'll not be, let me see how one can do that. There is some examples which were there. I'm sorry. Yeah, I think with this dynamically you can optimize the weights of the antenna elements using historical data and perform adaptive optimization of weights for specific use cases with unique user distribution and improve the coverage of a multi-cell scenario in the MIMO cell sites. And then this could be used for the network slicing also. I mentioned earlier that you need to do network slicing. This is one of the techniques which is used in the regular network configurations also, but it is very important and very useful when you are trying to combine the IoT applications where there is very low data rate and large number of devices, and then there is a high resolution video conferencing which is going on, which needs extremely high data rate applications, and then you want to use the same network architecture such that both are catered to within their requirements. So that is where you do the network slicing, and then you can use this a combination of I'll not go into how do we do this: analog beamforming, hybrid beamforming, digital beamforming. These are all techniques which are borrowed or which have been extensively used in radars, which in being used in communication systems also. There are chipsets available now for AI, and one can use those chipsets techniques which are there. Just an example was that Ericsson and Vodafone used MIMO hardware for radio towers to increase the network capacity at the additional cost of power, and then how they reduced the amount of power consumed by finding the information about the MIMO sleep mode when units are not active. It's a dynamic load. The subscribers will be using so randomly. There will be people using, not using in a certain sector, in a certain beam, in a beam directions. How do you optimize these things? And then when it is not being used, can we put it onto a sleep mode such that you conserve the power? Amount of power utilized is so large that you can do that. They tried with 6 trial radio units and then used machine learning algorithm, and just quickly go to the result. And then this sleep mode machine learning management delivered, it increased 14% saving in the energy consumption at each site. It's an enormous amount of power that is being saved in using that. And then there was another example of massive MIMO and cognitive radio supervised learning, pilot contamination problems. I'll not get into these details, but this is, you can use all this channel state information and location information, and then you can increase the efficiency of the system. And whether you use, if you get into the details of how the machine learning techniques are used, whether we use a supervised learning techniques or whether you use unsupervised technique, that depends. And the algorithms, which there are hundreds of algorithms, which is the best one to use, that one has to work on that. And then we will get into that. Then we will use unsupervised learning techniques, cell clustering, reinforcement learning, and then obviously we have this 5G core, network slicing, network function virtuality, and dynamic network slicing. So these are some of the techniques. I think they by themselves are big technology areas: network function virtuality and software-defined networks. So I'm using them in a slightly loose inter-exchanged terminology, but there is fine distinction between them. But let me skip at that. But please remember, network function virtuality and network slicing are critical components in the 5th generation communication system, which is being used in the core network part of it. The beamforming, which I used mentioned about AIML, which is used, is in the access part of the network, that is on the beamforming part of it, multiple input, multiple output, massive MIMO technologies. This is just to give you an idea of the 3GPP 5G roadmap. This is the release which happens. In fact, July 3rd of July, the 3GPP meeting was there. They frozen the release 16. Most of the things were frozen, and now there will be work which will be continuing certain part of it, and release 17 will go, and then people will start working on release 17. The 16 will be, and these are some of the areas most likely 17 candidates which are likely to come in the enhancement to the 5G NR IoT, the new spectrum over 56 gigahertz. There are more features which are unlicensed spectrum which will be used. These are some of the new methods, new technologies which are likely to come in the release 17. And this is the ongoing release time. As I mentioned, July 3rd, the meeting was there. Every quarter there is a meeting. They take the assessment of that. So these are the new technologies which are coming up. And then in the standards body, there is a Telecom Standards Development Society India. This works on standards looking from the Indian point of view. Indian requirements, they are working on that. And this is a joint work, collaboration between D-2, MEIT, Government of India, and Telecom Standards Development Organization. Just to give you an information, this is balance. I'll just leave this part just to say that when we say that these are the technologies, that doesn't mean that's the only technologies. Some new sudden thing will come up, and you'll have to keep an open mind to learn these new things and then work on this. This is the one which is there. And then thanks for listening. This concludes my talk. I'm open for any discussions and questions. Thank you.
Sir, the session was very informative. We have some questions which has been asked by the participants, sir. Shall I share, sir?
Yeah, sure, please.
So the first one was, sir, this was asked by Professor Satyashrikant. What is the difference between homogeneous and heterogeneous networks?
Oh, okay. I mean, there could be several definitions, but the one which I mention is that homogeneous is if you are using the same standard, particularly with respect to when I use heterogeneous networks or head nets, when I said it is in the context of if the network uses 3GPP standards like the 1G, 2G, 4G, usually they are all 4G is compatible, backward compatible with 4G and 3G, and so all of this whole family of networks which are there when you use with these mobile communication systems, then we call that as a homogeneous networks. But if you have dissimilar networks like the Wi-Fi, which is 802.11, in that it could be A, B, G, H, different standards are there. If you use only Wi-Fi in that itself, it is a 802.11 Wi-Fi N network, or it is the G network. That is again a homogeneous network. But the heterogeneous network comes when you want to build a compatibility between the mobile 3GPP standards of 4G and the Wi-Fi, or between Wi-Fi and a Bluetooth, or WiMAX and let's say 3GPP, so 4G communication systems. These are the heterogeneous networks.
Thank you, sir. There is one more question, sir, from Venkataramana. How to start research on current 5G communication? How to start research on current 5G communications?
Okay. I mean, there are, I don't know exactly how to tell, but the best way is to first identify or narrow down which area of the 5G network you would like to do the work. because 5G is a huge area. There are several parts of the network. You want to confine to only the access part of the network, or you want to do on the RF part of the network. Uh, because even in the access part, whether you want to do on the RF, you can take some research area in the power amplifier part of it, which itself is a huge requirement which you have to do. How do you linearize the power amplifier? How do you reduce the interference which will come when you are using a 256 QAM or some such area, or on the protocol area, or in the whether you will use some of the higher order modulations like 256 QAM or some such thing. What are the new kinds of modulation schemes and the waveforms you can do that one? Or on the protocol area itself, you first have to find out where your core strength is, or in the background of what you have, and then narrow down to that part of the area, and then find what has been done so far, and then what new thing can be done. So you can then identify the research area in those things.
Thank you, sir. There is one more question, sir.
Yeah.
Does any other countries are into the advanced technology more than 5G?
This is interesting. Lots of people claim we are working on 6G, but the generic term which is being used, and it has been almost sort of standardized in even standards bodies or internationally, is they call it as beyond 5G, because there is nothing called 6G. See, these terms 5G, 4G, 3G are designated after a certain work has been done and accepted, and say that this goes into this bucket. So 4G work, they say even, sorry, 5G work somewhere in 2004, initially people were talking about it, and last 10, 8 years, actual work has started. The work groups were created. There are people who are working on this part of the segment, that part. There is something known as 3GPP RAN radio access network. There is one on the core network. There are on several standards on several part of the security. Each one is working. So that comes, and so definitely the answer, short answer for this is that there are lots of people working beyond 5G, but which goes into 6G is absolutely no one knows. I mean, if someone says, I know this is going to 6G, I am sure that they don't know. They are just saying that. Because some of the advancements which are being right now done, there is no doubt there is a lot of research work which is going beyond what has been identified right now. Whether that could come in the next version of the 5G itself, or that qualifies for the next generation 6G, we don't know. That time will decide. And the significance of that new work, it is a dramatically new thing, probably it will move into the 6G. Otherwise, it can be an extension of the 5G itself. Because even in 4G, you see that initially some work which was done, they called it LTE, then they called it as LTE advanced, and then they called 4.5G for all fractional part of the 4 was coming into the picture. So now some things have been very clearly identified 5G. What? Because this is not the end of 5G. There will be another 100 things which will be coming in 5G. So all the new research which is being done, whether it goes into the advanced version of 5G, we call it as advanced 5G or 5.5G, 5.8G, we don't know. Or is it so good, or it is later it comes beyond a certain time, it goes into the 6G. We don't know, but research is going on beyond whatever I have spoken. There are lots of research going on.
So, can we take last question, sir? There is one more question. Okay, so the last question, sir. Can current 4G infrastructure can be used for 5G?
Yeah, there is that term which I used known as standalone 5G and non-standalone 5G. So non-standalone 5G works closely with 4G. So 4G, certain enhancement in the software and some augmentation in the uh, 4G networks, certain retrofitting of certain things, you can make that compatible and make that work. But the standalone 5G part of which predominantly that is in the millimeter wave frequencies, that will be exclusively the 5G. But otherwise, most of the time it is done such that the backward compatibility is there between any generation of communication system. There is a certain amount of retrofitting which can be done, but then, as I mentioned, NR, that is the new radio, which definition is instead of 15 kilohertz subcarrier spacing, it has all the way up to 240 kilohertz subspacing. Some of these things, that box which was used as a radio part of it has to be replaced by this one. So some parts, yes, compatible, and it can, some parts you'll have to bring new things. The massive MIMO and few other things. If it is just a MIMO extension to from 4 antennas to if it is 8 antennas or something, but if you want to 128 antennas and associated supporting protocols, then you'll have to use. So the answer is yes and no. Some parts yes, some parts no. And of course, the infrastructure, the base station things, the towers and other things will be definitely, one can definitely use all those things. But there will be several small base stations which will be coming. Like you have a telephone, street light poles, you can put a base station on top of that one. That kind of small cells will be coming into the picture in the 5th generation.
Thank you, sir. Thank you. We have got positive feedback also, sir.
Okay.
A nice presentation. Some feedback I'm just informing, sir. Informative, very nice session, interesting and informative, nice webinar, sir.
Thank you.
And
Thank you.
yes, I just request all the participants. We have given a feedback form in the chat box. We request all the participants to kindly give you a feedback for the today's session. And we would like to thank Dr. Kori sir from the organizing committee member for accepting our invitation in spite of sir's busy schedule. Whenever we approach sir with a program proposal, sir has given a positive thoughts and actively involved in all the programs, sir. So thank you very much, sir.
Thank you. Thank you very much for patiently listening to me. Thanks. And also, it's always a great pleasure to interact with your institute. I'm always delighted and I'm always available. Thanks.
Thank you, sir. Thank you. And we would like to thank all the participants for your active response. And I request all the participants to join for the afternoon session on a research topic called as Emerging Research Opportunities in 5G Wireless Networks. Will be handled by Dr. Jijesh DJ, Associate Professor, Department of ENC, SVCE, Bengaluru. We would like to request all the participants, please subscribe our YouTube channel, STTP, ECE, SVCE, and please click on the bell button so that you will get a notification whenever we start the session. Thank you. Thank you, sir, once
and
again.
And also, one more request, in case someone is not able to ask the question or didn't get the clarification, you can always feel free to contact me, M.H.Kori@gmail.com. It's a simple email ID. Please write to me anytime. Feel free to send me the questions. If I know, I'll answer. If I don't know, but I definitely know people who know that, I'll get the answers for you. Thank you.
Thank you, sir. Thank you once again.
Thanks. So I can drop out?
Yes, sir. Yes.
Oh, thanks. Thanks for all the